Hello guys, today we have another lecture about generating functions. I'm glad to see you all. I hope you're all watching, be it my groups or other professors' groups, and I hope you will enjoy it and will get much useful information on how to solve problems. Before starting the video, please go back to your lecture slides, review them, okay? They are providing you useful examples, okay, how to approach these problems. Okay, let's start with this recursive problem. So find the generating function for this recursive function, which is gn equal 6 times gn minus 1 minus 9 times gn minus 2 for all n greater or equal than 2. Okay, and with initial conditions, g0 equal to 1 and g1 equal to 9. Okay, so how do we approach this problem? Well, first let's define our generating function, right? So I'm going to write that let g of z, remember that the big G, right, indicates for us the generating function. So I'm going to say that big or capital G of z is, or let b G of z be the generating function for Gn, okay, or sequence Gn. I'm gonna write for the sequence Gn, and I'm also say with convention, okay, with convention that Gn equal to 0 for n negative. Okay, so what does it mean? So it's basically like an established thing, right, agreed upon. That is, if n is negative, right, n minus 1, n equal to minus 2, n equal to minus 3, then g minus 1, g minus 2, g minus 3, and so on, so forth, right, all of them are equal to 0. So this is the convention that we're using. Okay, so I'm defining my g, capital G of z, to be generating function for sequence of Gn, or in other words, I'm going to write it like this, right, by definition. G of z is equal, okay, the sum of z to the power of n times g of n, and over here my n. So this is by definition, right? Now, what I will need to do is I will need to, okay, consider this recursive function, make it into a more general one, including initial conditions, and then what? Multiply by z to the power of n and take the sum and make it into a definition, right? Somehow to get g of z. So if I can get, okay, if I can make it into a definition form like this, then I can substitute for that g of z, right? And then I can derive my generating function, okay, for the recursive function. So let's write it out. Now I have my function, right, gn equal 6 times gn minus 1 minus 9 times gn minus 2. So multiply by z to the power of n, okay, both sides. So it will give me simply z to the power of n times gn equal 6 times z to the power of n gn minus 1 minus 9 times z to the power of n times gn minus 2. Now, the question about what about initial conditions, right? What about when n, so this is, remember that for n greater or equal than 2, right? And also in this one, right? But what about when n equal to 0 and n equal to 1, right? Remember the initial conditions, right? So we have not incorporated these two into our general recursive form, right? Since this is only true for this n greater or equal than 2, right? So, okay, then let's consider when n equals 0, what do I have, right? So let's consider the original function, right? Recursive function. So n equal to 0, I will have g0, okay, times or equal 6 times g minus 1 minus 9 times g minus 2. And remember, by convention, right, this is equal to 0, and this is also equal to 0. And by the condition of the problem, g0 is equal to 1, right? So I have 1 equal 0, right? Or 0 minus 0, which is not true, right? Not true. So therefore, it begs for us, okay, to make a correction in this case. So we have to make a correction. Make a correction term okay, or introduce a correction term, which is to make it equal, right? So to get 1 equal to 1, we need to add 1 basically, right? So make a correction term, that is add 1. So in that case, what happens is simply g0 equal 6 times g minus 1 minus 9 times g minus 2 plus 1. All right? And when g minus 1 and g minus 2 are 0, I will have 1 equal to 1. All is good, right? Now, let's consider the second case when n equal to 1. So when n equal to 1, I will have g1 equal 6 times g0 minus 9 times g minus 1. And I know by the condition of the problem that g1 is equal to 9, right? 9 equal, and g0 is equal to 1, so I have 6 times 1 minus, and g minus 1, this will be 0, right? So I will have 0. So basically, again, I have 9 times 9 equal 6, which is not true, right? So this is not true. So we have to again introduce a correction term, right? So add a correction term So, and correction term in this case will be 3, right? Because to make it equal, okay, to make it true, we need to add on this side 3. So basically, I will have to write it like this, right? G1 equal 6 times G0 minus 9 times G minus 1 plus 3. So if I add this 3 correction term, then I will have the equality to be true, right? 9 equal 9. All is good. Okay, but the problem is, how do I incorporate this, okay, 1 and 3 into a more general form or into this expression? Okay, so now we'll have to introduce binary function. So introduce binary function given by square brackets, remember? And inside the square brackets, we have to put the condition. And what conditions do we have? We have 2 conditions, right? One is when n equal to 0. The other condition is n equal to 1. So when n equal to 0, we should have value 1, right? The function should give us value 1. And when n equal to 1, the function also should give us, but the value should give us is 3, right? But remember that the binary function only gives us value 1 or 0, right? So what we need to do is simply, right, multiply 1 by a specific coefficient. So what I will write is simply z to the power of n times gn equal 6 times z to the power of n gn minus 1 minus 9 times z to the power of n gn minus 2 plus, okay, z to the power of n equals 0. So I'm introducing this correction term, right? When n equal to 0 specifically. Because when n equal to 0, I don't want, okay, my correction term to be added for this case, right? I only want my correction term to be added, and when it is equal to 1, right? When n is equal to 0, I only want correction term to be 1, and only for this case. And I also only want correction term to be 3, and only for this case, when n equal to 1. Okay, so therefore, I'm putting this condition inside the bracket. So that is, and when n equal to 0, this condition is true, and the value of this binary function, right? So remember, it is 1 or 0, right? The value of this function will be 1. And when n equal to 0, z to the power of n will be 1, right? So this is simply 1. 1 when n equal to 0. And another correction term is z to the power of n when n equal to 1, right? And when n equal to 1, the condition is true, and the value of this binary function will be equal to 1, right? But in this case, I need a correction term to be 3, right? So to get 3, is simply I will multiply by 3, right? I will put 3 in front of this expression, and that's it. And when n equal to 1, this whole expression will be simply 3z, right? Z to the power of 1. And now we're ready to find the generating function. Okay, so remember, by definition, right? By definition, that g generating function is given like this, right? Now we have incorporated all the values of n, right? And over here we should say greater or equal than 0. What I can do now is I can take the sum, right, over all the values of n on both sides. So remember that we're gn, we're considering as a sequence. But if we want to consider all of the terms, right, of the sequence, or add them all up, then we need to, okay, express it as a sum. So basically I will write the sum of z to the power of n g n, okay. Over here I will take 6 outside, and I'll write it simply like this. And same logic for this one. 9 I'm gonna put outside the sum. Okay. And I'm gonna also apply the sum for these terms as well, right? So this will be n plus 3 times the sum of z to the power of n when n equal to 1. Now, if you pay attention, you see that this is already g of z, right, by definition. So this is already g of z. Great. Now, what about this one? I want to express this one in terms of g of z as well. But the problem is that I have index to be n minus 1, right? But I need the index to be just n, simply. So what I can do, I can simply move the index, right? But in essence, what is happening is basically if you try to expand this one, right? Open up. When n equal to 0, right? What do you have? You have, let's write it like this, right? If you expand this, when n equal to 0, you have z to the power of 0 times g minus 1. When n equal to 1, you have z to the power of 1, g 0. When n equal to 2, you have z to the power of 2, g 1, and so on, right? And remember that by convention, right, we said that g of negative value, of negative index, right, g minus 1, g minus 2, and so on, are all 0. So this is 0. And so we are starting with this one, right, z to the power of 1 and g0. And after that we are going with that z to the power of 2, g1, and so on. So this is 0, and it basically doesn't affect the sum. I can leave it out and start immediately with this one, right? So if I start with this one, what I should get is I can write it simply like this, right? The sum of z to the power of n plus 1 gn, n still starts with 0, right? So when n is equal to 0, I have g0, z to the power of 1, right? When n equal to 1, I have g1 times z to the power of 2, and so on. So all is good, right? We're just leaving out that term when g is equal to 0, right? With the negative index. Okay, so the same logic I apply over here. So it will give me 9 times minus 9 times g. Now over here I will have z to the power of n plus 2 g n, and these ones will remain the same. Okay, now if you pay attention, you see that over here z to the power of n plus 1 is simply, right, is simply z times z to the power of n, right? So that means that this z does not depend on n, that we can take it outside of the sum, right? It's as if as a constant. And the same logic for this, that the z to the power of 2, we can take it outside of the sum, right? And therefore now we're going to see that we have actually, okay, come to form the function g of z according to its definition. Okay, so I'm going to continue on this side. So I have g of z equal 6 times the sum of, okay, I am taking outside z, so I have z to the power of n times g of n minus 9 times z to the power of 2, right, outside of the sum, and I have over here z to the power of n times gn, and plus the remaining terms, z to the power of n when n equal to 0, plus 3 times the sum of z to the power of n when n equal to 1. Okay, great. So this one, right, is gz, yeah, g of z. This one also g of z. So I can simply write g of z on the left side is equal 6 times z times g of z, right? 6z times g of z minus 9z squared times g of z. Great, right? We're expressing all the terms in terms of g of z, or in terms of definition, right? And what about this one? So remember that this sum, right, only is valid when n equal to 0, right? What does it mean, only valid? It has only value 1 when n equal to 0, because this is the condition. So when n equal to 0, this function will be equal to 1, right? And when n is not equal to 0, the value of this function will be 0. So it simply remains for me just to write when n equal to 0, it will give me only the value, right? And when n equal to 0, this will be 1, and z will be simply z to the power of 0, right? So this is 1, and this one z to the power of 0, right? Multiplied, which is 1. So simply, I will write 1. Over here, the same logic, right? This sum is only has a value when n equal to 1. When n is not equal to 1, the binary function, okay, gives me value 0, and the whole thing vanishes. So only when n equal to 1, I have some value, and which is going to be 1 for this, and z to the power of 1 for this, and I have 3 outside. So basically, I will have 3z, right? And I'm going to write over here, therefore, 3z. Okay. Now what is left to do is to collect all the terms with g of z together on one side, and all the remaining terms without g of z on the other side. So I'm going to move this, okay, to the left side. So I simply have 9 times z squared minus 6z plus 1 times g of z, right? So I move this and take outside g of z. And on this side, I have 1 plus 3z. And from this, I can say my g of z is equal 1 plus 3z divided by this expression, and which I can also simplify further if I want. I don't have to, right? Oops, minus, like this. So that's it. This is how we find generating function. After this, okay, in another video, we'll see how we can actually use generating function to find a closed form for recursive functions. Remember, this is one of the methods to find closed form for recursive functions, right? As repertoire, as perturbation, as guessing, right? And all the other methods as well. So I hope this was useful for you guys. Please watch it again if it's not clear. If you have any questions, please feel free to come to me, ask for clarifications, for additional problems if you want. And I'm glad to help you. So see you guys. And if you see me, okay, between the classes, even if you're not my student, please say hi, and see you all.